Okay, so we're going to be continuing with the second of the tool sets that are in this section on profiling and profile analysis. This is going to be on ScoreP and Cube, which is the browser that goes with the tools to view the profiles. And it's going to be presented by Mark Schluter from Jülich Supercomputing Center. So Mark, you're ready to go?
I'm ready to go. Thank you. As Brian mentioned, my name is Mark Schluter, and I will start out today in the second part of this morning's session with the ScoreP measurement and instrumentation system. Just to get you back to the performance engineering workflow and how our tools are arranged in that. We basically have the ScoreP, which we start out with, which deals strongly with the instrumentation and the preparation stuff and the measurement itself. And then later today, I will show you the Cube, which will go into the analysis of profile data, which is the target for today. And what we see tomorrow is basically going then to tracing and doing analysis with Scalaska. And I also will probably show a few slides introduction on Vampire to get the full picture. To get started with ScoreP, some general information. It's, as mentioned, it's an instrumentation and performance measurement infrastructure, and we are using both the methods of profiling and tracing. One for the call path profiling, we recorded in the cube data format, and for the event-based tracing, we're going for the OTF2, which is a general tracing format that is publicly available. While looking at the supported parallel paradigms, we are going for multiprocess in MPI and SHMEM. Also, most example you will probably see is MPI. And on the thread parallel side, we support OpenMP and pthreads. And technically, the way we are intercepting information, a lot of threading models that are pthread based, where we still get the underlying pthread, we get also some information out of it. And on the accelerator side, CUDA, ROCm, OpenCL, OpenACC, and Cocos, which provide additional information from the CUDA side. Talking about general software design stuff, it's open source. We are portal and scalable to all major HPC system. It was originally a project funded by the BMBF and had some collaborations with the US on various projects. And this is basically an infra scheme how our components interact. If you're looking at the top line, you basically have the motivation why ScoreP was created as a shared measurement infrastructure, because we are supplying event traces and cube call path profiles for various tools, Vampire, Scalaska, and Cube, which we will see in the next 2 days. But there's also other tools that use cube format like Tau, XtraP, and TauDB. And underneath is the measurement infrastructure, which will be attached to your application run, which provides access to the various paradigms, and also additional support for counters. The most common use is probably PAPI, but you also get R usage perf. And we have a plugin interface that allows you to additionally use an interface to write your own plugin or use external plugins to connect to other sources. In terms of supported languages, we are supporting C, C++, Fortran, and Python for our measurements. On the organizational level, there are quite a few partners, and they're basically matched towards the tools that are using ScoreP for their measurement instrumentation, and there were the partners in the original construction of from ScoreP. This should basically serve as a starting point before I now want to go into a demonstration how to actually get measurements. Brian showed yesterday some examples where he shows the results of measurements he did with Scorpy, and now we want to see actually how to see the workflow, how to get there. And for that, I will do a short demo on an example that also Cedric used, BTMZ. It's not an exciting benchmark, but it's well used and established as a tool that we can use for our demonstration purposes. So the first step we probably always recommend doing is a reference run. While Cedric mentioned that with the sampling approach Macau uses, you have relatively little overhead. With the instrumentation approach that Scorpy uses, we tend to get more overhead, and we need to justify and check how much of our overhead is introduced through instrumentation. So the first step is doing measurement without any instrumentation. And this is just, as you can see, an MPI and OpenMP hybrid measurement that we are running, application run. And the other point that is useful while you're doing uninstrumented runs is also to ensure that the configuration you have chosen with your code and the system actually work in the current configuration before introducing more complications through instrumentation with another system. I'm currently running this demonstration on Eureka, one of our systems here in Jülich. But in principle, the principles hold the same for all systems. And so this is the standard Slurm script. We don't need to get on all the details. Just running the BTMZ in a certain configuration of 8 processes and 6 threads with OpenMP set to the number of threads. While we're waiting for the job to run, a few more mentions. The reference time, in this case, the reference time is provided by the application code itself because it measures its internal wall clock. But getting any kind of wall clock time, even from external tools, is totally fine because we don't need exact measurements here on this level. It is enough to get a general overview of what the runtime is. And in this case, you see the output that is the same or similar as the one Cedric had with BTMZ. You have the time steps running through the application, and then in the end you get a time in seconds of something about 14 seconds, which is a short run, and for most actual performance analysis steps, you should probably run something a bit longer because just for statistical expressiveness. But since it's a demo, we want to keep it concise and have a bit of short turnaround times. So on the left side, I basically show you how the workflow builds up and how it fits into the different steps of the performance cycle. And I would generally categorize the reference run as something of a pre-preparation step, since you don't necessarily need it to run every time you're doing optimization runs through the cycle. Just if you're changing the larger picture of your application, then you probably need another one to get settled. So the next step in this workflow is essentially going into the instrumentation step. And with Scorpy, the default way to instrument things is to prefix any compile and link step with Scorpy. So we prepared this for this demo example so that we just have to use a variable prep to and then all the compile commands will be prefixed with score P. Note this score P will recognize that this is an MPI application, and with OpenMP, based on the arguments supplied, if anything doesn't work out as expected, you can also specify all the paradigms you want to measure as a parameter explicitly on the command line, or if there are options or variants you want to choose. But in general, the Scopy tries to recognize what you want to do and measure, instrument, and links to the correct libraries. So the instrumentation ran through the same as before. And now if you want to look at the executable, it's the same. And you could run it just like this without any additional options. Just to, if you want to check if it's actually instrumented, you can use LDD because we link basically our libraries to this executable. And since our libraries are basically on paradigm level, you can see actually which paradigms are linked into it. You have MPI, you have OpenMP, and compiler instrumentation, for example. This depends on what your Scopy configuration looks like, but it's a good check to see if you got the instrumentation you actually expected. And now we want to run this, and our job script looks essentially the same. Here are a few additional environment variables, but for a plain run and the initial one, you don't actually need them. I generally recommend setting the experiment directory simply to have a speaking name. In this case, it's just the BTMZ with the number of processors and threads. But otherwise, you have just the OpenMP num threads that you already needed for the plain run and run the same job as before, which is essentially the next step in our workflow, the first instrumented run. And this basically starts the measurement phase of the optimization cycle, where you see that this will be running for a bit longer because we are running with a lot of more overhead than we had before, and we want to see how much of it. While this is running, I can show you if we are looking at the help output of the Scopy instrumenter, you can see they have options to set the threading paradigm. You have the options to set the multi-process paradigm. So in case you have any issues with these options getting recognized automatically, you can choose them on the manual level. And also, when we are speaking about configuration of the environment for the measurement run, Scopy Info is a tool that we provide with the installation, and with the set of config vars, we can see what config vars are available if you want to modify the measurement run. And you get a full list of the variables that are available for this installation of Scopy. You get basically the name of the variable, short description, and the default value. And depending in particular if you have various options, it's quite helpful to see what the default values are and how you're getting them. While this is a long list of variables, in most cases, you just have to set a certain handful of variables. So the run is through, and let's see the output. And here we see that the time in seconds went up to 39 seconds basically, which is far longer than the original 15 seconds of the uninstrumented run, which shows that we need to check the overhead and see how to refine the measurement. And this comes basically to the next step in our workflow, where we do the quality check of the measurement and do something called scoring, where we use a tool named Scorpi Score and run this on our measurement result. And we can see information which gives hints about the expected overhead. When talking about overhead, we basically have two topics we are talking about. One is the overhead in terms of time, which is we measure by the comparison of the wall clock times. And one is when we are looking towards tracing, which we cover more tomorrow, which is the expected memory requirements for tracing, and which is something that is in the expected total memory. And this is something we can see here. Without any further modification, we would expect to use 21 gigabyte per process, which is way more than the maximum of 4 gigabyte we support with our internal memory management. And even just to say it, in most cases, if you actually need to use 4 gigabyte of memory for SCORP, you probably should refine your measurement a bit more. The other aspect of overhead is the time overhead, and there this column is most interesting, the time per visit, because time overhead we introduce is basically dependent on every visit and is static for every visit. So if you have a region as a function call which is very short, in its execution time, the overhead becomes proportionally way larger than it needed to be. So this is the reason why for the time overhead, we need to bring down the contributors who have very short time per visit and become called high number of times. So if you want to find the actual culprits for this, we can use the option -R, which lists us the contributors to the overall overhead by function or region, but mostly is its functions. And if you're looking at this table, they're sorted by max buffer requirements, which is interesting for the tracing side of things. And we have at the top of the list, we have 6 functions that are heavily contributing to the amount we are spending on the number of events that we are generating for these. And they are all are spending a very little amount of time in each of the instances. This is in microseconds, so it's less than 1 microsecond per call. And these are small function calls that we do want to filter out in this. And filtering means is that we attribute this to the parent of the region and is relevant to reduces the level of detail, but not the information. Another element which we have in this table is the type classification, which is you have paradigms like OpenMP, MPI, and then we have user and COM. User and COM are both compiler instrumentation which reflect the function calls and the call tree of the user code. But the distinction is basically, which you can see on the left side here, user calls are on passes where only user calls are, while the combined ones are on paths to other paradigms like MPI and OpenMP. And why is this relevant? This is relevant because these call paths basically in our result structure provide context to separate different MPI calls out from each other. Once you filter out these ones and basically combine them on the base level, you lose this distinction. So we try to keep these in the measurement to give the most amount of information we are getting out of it. So the first candidates for filtering are always user functions and that have a low time per visit and contribute highly to the max buffer requirements through the number of visits they provide, basically. So, and next question would be basically how to create a filter file that we can use then to refine the measurement. And for this, we have added in recent years a generation option that provides an initial filter file for the measurement. And this is the option -G. And this basically runs the Scopy score and then tells you a bit how to use it. Essentially, it sets you have to set the environment variable Scopy filtering file and then use the filter file you want to choose. And the generated file is called initial Scopy filter. And if we look at it, it provides information about how it was generated, but also then contains in the syntax for our filtering files the names of the 6 functions that we identified as the most relevant cases. And as comments, we added also the information from the scoring, basically why they are excluded. In the header, basically, there's also information how the default generation parameters are. So 1% of the estimated trace buffer and less than 1 microsecond time per visit and type of user region. You can modify the parameters by yourself if you want to refine it on that level, or you can add in this text file additional functions to filter out to refine the process. But for the moment, on this level, I think using it is just fine. And we want to know, okay, we have a filter file, but how good is it? Technically, you can just use it and rerun it, your measurement, and see how effective it is. But Scopy Score also provides the option to preview the effect of the filter file. So we are going with the -F for the initial filter file. We're using -R to get the region level, and then we are going again on our profile file and see what the Scopy score output shows. And for one, the expected memory requirements per process are just 100 megabytes, basically, which is way less than 21 gigabyte. And we see now here the column filtered, where plus is it's filtered, a dash is not filtered, and a star is if they're mixed elements. And we see our filter file effectively filtered the functions and the result out of it. This is particularly helpful if you have something like complex C++ function names to see if you actually hit your filter names, and since the name matching can be sometimes a bit tricky. So next step would be basically to run this measurement with this filtered file. And for that, we have to edit our job script. In this case, we're using the initial filter file. Another point is we want to measure hardware counters. Since we're adding additional elements anyway, we are doing it right now for this run. And we are using POP3 counters. And so far, we are using the environment variables copy metric POP3. In this case, total instructions and total cycles. These are the names that POP3 itself uses, and they are comma separated and just listed. You have to be aware of consequences. Adding counters tends to get more overhead. It also increases the trace size, which we can preview if we are. Yeah.
You had a typo in the name of the cycle counter.
Oh, got something lost at the end. It's a cycle.
CY. I think it was CYC. I don't remember myself.
Yeah. That got lost in copy-paste activities. So since we are looking at Scopy score, it might be interesting to see the effect of counters in your measurement. We can basically say we want two counters and see how this affects our measurement with our filter file and the current measurement setup. And we see that from 100 megabytes, it went up to 215 megabytes expected trace memory, because we basically add additional events at each enter-exit, and so you have to consider them as additional information that you need to introduce, keep track of. So now we can run the job. And basically, it will hopefully, since we are now filtered this, it should run faster than the unfiltered one. And while this is running, we can also see, since we didn't change the name, the old measurement got renamed and the new measurement got the name that we are currently chosen. And as files that you find in it is the profile file, which just is the result file which we later will be looking at also with Cube. Then there's also a Scopy config file, which contains the used config, which is a complete listing of the environment in respect to Scopy. It's mostly default values, since we didn't set that many values. And the manifest file is basically a piece of documentation, which files you should expect in your measurement. It's quite helpful by debugging. And in this case, it also lists the variables we actually set explicitly. So if you want to rerun something, you are aware of what was set. It also includes the Scopy filter file we included. Just to mention, on the left side is basically a summary of the filtering process, and what I'm running through on a similar example, but not the exact same, but on from a prior training. So now we basically have the filtered result. And if we are looking at the output of the BTMZ run, we're now seeing we're coming back to the 15 seconds, so a slightly longer run, but that also could be a run-to-run variation. So there's basically no overhead at this point, because we filtered the big cases out of it, and we now can technically use it. We could right now look at it, but before we actually consider the profiling to be a technically complete result, we do a first post-processing step called remapping, which adds additional information and metrics to it. For this, we're using the tool Cube Remap 2 in this case. Minus S and minus D are options. Minus S is adds additional metrics, and minus D does pre-calculations of certain values, which is basically a trade-off between how large the cube file is and how much effort is it to calculate the analysis in later on. So we're trading basically towards additional space by pre-calculating values. And additionally, there's also topologies that are created basically from the data of which kind of system tree information we are having. So now we have a remapped cube file, and without any additional output file names, this is by default remap.cubex. And this should be our final result, which for the profiling. So we basically now could start the profiling, looking at it with Cube GUI, and that would be the next step in our presentations. But just to give a bit of an outlook at this point, it can be, while this was a relatively straightforward step-by-step linear workflow, it can get more complicated if we are out in the wild with various applications, systems, and software environments. For example, depending on how much of your variations of your options, you have to rerun your measurements multiple times to get what you actually want to see. You might need to use the filtered file that you get from your runtime filtering and use it for compiler instrument filtering, compile time filtering, because it will still reduce additional overhead if it's still a problem. Some measurement systems, build systems like CMake don't like prefixing of stuff. So we're providing compiler wrappers like Scorpy-MPICC as complete compiler replacements that you can work with. There's also, we generally recommend people using libraries for optimized like mass libraries, MKL and such. But if you're running your application, you generally don't instrument these, build them or instrument these. And you don't want to because it's not the code that you are intending to optimize. But if they are not instrumented and not included in the measurement, you don't actually see the time spent in these libraries by default. And so the way between nothing and a complete instrumentation is a method of user library wrapping we provide, which is a slightly manual process of wrapping headers so that you get basically black box function calls for whatever mass calls or library calls you are going out to, so you can see, okay, this is done in this section of code, and that is belonging to this library. And on the analysis side, aside from the GUI itself, we have also a set of command line tools that provide, you can mostly for dumping information directly to command line and further post-processing, or if you want to deal with multiple cube files, merging them or doing an average, it's useful doing this on the command line. And something that we then go tomorrow is Scalaska and Vampire. I'm just mentioning these as very highlighted, short, one sentence topics because there are wide variation of areas you can get into, but they are very specific to specific applications, and they're going beyond the scope of this introduction. If you're getting later access to the slide set, you will see that at the end there's a set of reference slides that basically go with 1-2 slides on various of these topics to basically get an idea how to cope with it and as a starting point for further investigation. Now, before leaving the command line, I want to start looking at the POP metrics that were mentioned in the introductory presentations yesterday, because with the basic profile we are measured today, including the PAPI counters, we can get a good set of information out of the result also for the POP metrics. And we can use this as well on the command line as on the Cube GUI itself. So because of that, I wanted to show you how to do it on the command line first, and then when we switch to the cube side of things, we can see how it's done on the GUI side. It's also a cube tool, so it starts with cube underscore and then pop metrics. For the standard metrics that we showed before, we are using the analysis VSC, which is basically the going with the same set of metrics as the VSC tools use, and then our remapped file for the measurement. And we are getting basically command line output of our metrics. And as you saw yesterday, you get elements like the load balance, communication efficiency for MPI, OpenMP. Since this is a purely MPI, OpenMP program, we're getting no GPU metrics. And for some elements like the serialization and transfer efficiency, we need the tracing on our side. So we see that's something we see tomorrow. Additional metrics like the IPC are there because we got the information from the PAPI counters. Yeah, and I think this is a good point to leave the SCORP side of things. This is just things. And we now will switch to the cube element of the presentation. Just as a short information, if you have questions, we have documentation on scorpi.org. There's also further presentations on VHPS of past trainings. And you can always mail us at support@scorpi.org. Yes. Okay, let me switch a moment. Now we will continue with the GUI side of things with Cube. And Cube is basically a set of tools that contain the command line elements with the library behind it and the GUI itself, which is currently running on Qt larger than 5. At some point, we'll probably switch completely to Qt 6. And this was originally developed as part of the Scalaska toolset, but in the process of going for different components, we was split it off out of it and is now released separately. Latest release is 4.9.1 from beginning of the year. And if you want to install or use it, there are various options. The classic options from installation from a source tarball. We provide right now binaries for Windows, Mac, and Linux app images. There is, I think, in the Fedora distribution, and as part of the POP3 project, we're basically making the Cube tools available on HPC systems as far as we can get them. And the most recent way of using it is Jupyter Lab and WebAssembly integration, but that requires system support. And when you actually want to open Cube result files, you can just copy the CubeX file, which is enough for that, or you copy the entire SCORP directory. Some files like the config are maybe used for reference inside Cube, so they might be useful. And if you have the source code on the same system available, you can link to the source code. The most convenient one for most cases is do a local amount of the remote file system and use the client locally, or use a client with a Cube server in the backend. So there are various options. The preferred method is basically have a local client and then connect to the remote files in some form. Conceptually, the analysis, presentation, and exploration works along 3 dimensions, which is where the name Cube comes from. You have on the one side a metric, a property you want to look at, then you have a call path and a system tree location. The property is basically the topic you're looking at, while the call path is the where it's located in your source code. So which MPI call is relevant, which OpenMP region you are looking at, etc. And the system side is, okay, well, how is the behavior on the system, on the processes, different nodes. The system tree itself contains a certain structure depending on how much information we're getting from the system. You may see the nodes, the racks, and planes, for example. And you basically explore the metrics along the lines of these three dimensions. The exploration is basically three coupled tree browsers. So all the information is in the primary form displayed as trees, where we have values for precise comparison, but also as color to get the easy identification of hotspots. And we are using heavily the exclusive model that was also mentioned yesterday, where we basically go through folding and unfolding the call tree and metric trees. We get the inclusive and exclusive values. Inclusive was basically if you have a function call, the inclusive part is everything below it, inclusive with sub functions. And the exclusive value is basically just on the level you're looking at. And with this, you get the option to get a variable level of detail depending on which elements of your call tree or system tree you unfold. Now we're going into demo part. The T-Leaf study, which is here in the slide set that you will get access to, is basically doing similar things as I will show in the live demo, so that we have something in the slide set at hand when you're looking later at it. So I'm switching to my other screen. So I'm using for this the Jupyter Lab of Jülich, in this case with X environment, basically for convenience. And I'm here in the directory where we have our two measurements and the remapped cube file. And now we want to look at the remapped file with cube. And now we are getting the three mentioned browser panes, which are basically the metric tree and the call tree and the system tree. They each have variants we want to look at. One of the things I mentioned before, the remapping is it's particularly noticeable in the metric tree because it adds metrics and subdivisions. In this case, it structures time depending on paradigm. So we have MPI and OpenMP. So these are the categories which are looked at separately. So if you are looking at the code, you have the looking at the MPI, you get the communication management and overhead, which is categorized by their function calls essentially. So the MPI is, for example, in the management part, just to mention something. And the computation is the useful computation time where you actually calculate something outside of the management overhead of other paradigms. You get also additional information about bytes transferred, etc. And since we are measured with PAPI counters, we see also the PAPI counters, the total instructions and the total cycles, which are on the here, and we're getting them basically as a symmetric counter metric for every enter exit. So we see the same call tree information for every call tree instance, the counter values in this instance. And on the third side, pane, we have the system tree. which in this case is Rilka, with we getting from Slurm some information about the switches and the racks, and then have two nodes with each 4 processes, and then 6 threads, the master thread and the OpenMP threads. As long as we are selecting this selection, we're seeing basically just the master execution. With the whole evaluation of our metric is from left to right. So we are selecting computation, for example. Then we are selecting the place in the call tree in some form of inclusive or exclusive look. If you're looking, for example, probably the most interesting part is something like the calculation here in IDI. And we see then this time distributed over the system tree, which can be, for a relatively small example, is easy enough to look at in the system tree by line, basically. But if you want to have large measurements, it is useful to look at them in a more efficient way. For example, you can look at these information in statistics form, where you get a box plot about the execution times that you are here looking at, or as a variation of the violin plot, which can see groupings of different execution behaviors. If you want to have a more visual approach, you can also use the sunburst, which is radial display of all locations. So you get basically a whole information just by color information in one view. Right now, we're looking at a color scale with a standard rainbow from blue to red. But since there are a lot of small function executions here, it's rather blue for everything. We have for each of these columns variations on the way we are looking at this. Right now, the default is absolute values, but you can also look at something like peer%, which shows more interesting behavior. Peer% is, in this case, we're looking on the level of threads, and the highest thread is the 100%, and all others show how much percent they're from the highest value distance. And this way you get see a bit more specific information, and you can look at the specific values right on each of these if you're looking into specific behaviors. A similar information level you get with topologies, which are generated through the remapping process. In this case, is this also for the process times threads, in this case with the node information. When we are looking, for example, we have 2 nodes. We have on the x-axis, we have the threads, and on the y-axis, we have the process. So we have our 4 processes, the 6 threads, and 2 nodes. And we can see behavior-wise that the distribution of load is not the same over all threads. The most used threads are the first 2 ones, and the others have a lower load. And we can see that is a behavior that is replicated in the different solver routines here. And if you're looking, can basically see also the inverse information. If you're looking at the OpenMP synchronization elements, we see that the threads that were underused have the highest synchronization because they are basically waiting more for work than the first 2 threads, which are working more, generally more, have a higher load. We are also having the option to calculate the metrics, as I mentioned, with the POP metrics. We can get the same information on the GUI level. Here's an additional plugin which is providing a visual solution for this. We're selecting the same analysis and calculate them for the current call path. As mentioned yesterday, it is useful for calculating these metrics on a specific focus of analysis and not just the whole measurement, because in particular, if you have initialization parts, you don't necessarily want them in your POP metrics. So picking a useful part of your metrics, focus of analysis of your subtree, then you are getting better numbers and more specific to what you're actually looking at. And you're getting essentially the same information as I showed you on the command line interface stuff, which is grayed out, is not available for this analysis because of information we are not adding. But we now have basically chosen a specific set of C nodes that call paths that we are calculating that is for. And since we are selecting, we can also select multiple and get the summary value for these. As I mentioned, we are have, as long as this compiled as a system and you have linked to the access to the sources, you also can see where specific functions are called in the source tree, and you have the option to basically link the information that you see in the call tree to your source code. These are the basic informations that you can draw from the measurement. We can go in more detail with various sub-elements of structuring it. You also can configure a lot of these features further if you want to go into more detail. But as a starting point for these kind of measurements, this is will work out fine. I think I will stop at this point, and we will see tomorrow a bit more what we are adding when we are using tracing. We will get another cube output report like this, but with added information from tracing. But we will see that tomorrow, and I think even if I'm a few minutes short, I think the level of detail is enough for the scope you are looking at here. If you're shortly going to the slide set, so if you're looking through if you're getting to access to the slides, you have basically the similar approach to what you can see in the different sample of metrics and what we are getting out of it with the different options. And we will see more of this tomorrow. And for cubed in general, the same things applies as we for score P. We have documentation on scalaska.org, which because it's part of the Scalaska general toolsets, and the cube user guide has also additional information. And if you have any specific questions to this topic, you can mail us to scalaska@fzulich.de. So at this point, I will probably stop. And if you have any questions, I'm happy to show you or explain something. And otherwise, thank you for your attention.